equations, numbers, figures, the record of quantity, and the language of science.
Many of the great questions of science are questions of how many, how large, how much, how heavy, and so on. For example, how many chemical elements are there? How large is the solar system? How long is the wavelength of light? The hallmark of scientific work is numerical measurement. There are some 100 elements. The solar system is 7 billion miles across. The wavelength of a beam of light may be 100,000th of an inch. Numbers, numbers, numbers. Are numbers really indispensable to science?
It wasn't always so. Nature has been looked at through non-mathematical glasses, and in branches of science such as botany or anthropology today, one can gain deep insights without using mathematics. But even chemistry and physics at their beginning did not pay a great deal of attention to numbers and mathematics. Before the rise of modern chemistry in the 17th and 18th centuries, many of the questions of chemistry were investigated through alchemy. What interested the alchemist about a substance was not its precise value of specific gravity or melting temperature, but it was rather the psychology of the substance. The alchemist thought that substances liked or disliked one another, and that this governed their behavior. Here, in his laboratory, the alchemist watched a chemical reaction in his flask, and he thought of it as a drama of sympathy and union, of birth, death, and resurrection. And when he wrote about these reactions, he wrote not in the form of the equations familiar today, but often in pictorial symbols. Here is an early 17th century method for purifying gold and silver. It's a cryptogram. The king represents the gold, which is to be purified. The fierce wolf stands for antimony, a metal which bites and devours the metallic impurities of gold. That is, it combines with them when the impure gold is molten in that crucible you see beneath the wolf. The process must be repeated 3 times. See the 3 flowers held by the queen. The queen, by the way, represents silver, and the figure of the old man, Saturn, stands for the lead, which carries the impurities to the bottom of the small vessel in which lead and silver are heated together. In early physics, too, this allegorical sort of thinking was used to explain or describe events which are now represented in mathematical language. For example, there were allegorical ways to explain the observation that fire rises. Lighting a candle and watching the flame grow upward, the scholastic would say that in the flame resides an essence whose natural and proper place in the scheme of things is to be high up above the earth. A flame shoots up, he would say, like a traveler hastening back to his home. Conversely, stones would be thought to be endowed with essences which produced in them the desire to fall down to the proper place toward the center of the earth. And in fact, before the ideas of Copernicus were accepted in science, all occurrences, both on Earth and among celestial bodies, were traced back to the conception that there's a natural order of things in the world. The Earth was considered as occupying the center of this great plan, surrounded by regions belonging to water, air, and fire. And as you continue outward from the earth, you pass through the regions of the moon, sun, the planets, and beyond the planets, the regions of the souls of the departed who have been saved, and of the deity. You can see it at a glance. The universe was thought of as a unified order, a cosmos, in which each thing had its proper place, and each part was connected with all the others. Here, too, the important feature was not mathematics, but the pictorial or allegorical or qualitative. Now, a good part of our common sense, our everyday thinking, still uses this allegorical approach to the world around us. You say to this day, an acid attacks metals, even if we no longer represent this graphically with the figure of a fierce beast. And science, too, might have gone on in this manner, though it would have become very different than it is today. But then something happened. Something happened in science to make it change, first gradually, then more rapidly, culminating in the work of Kepler, Galileo, and Descartes. And this something was the rise of an idea that the secrets of nature are written in a mathematical language, one that anyone who would understand science would first have to decode. Johannes Kepler, a German astronomer, said that God had built into the world the mathematical laws governing the motion of the planets, and also had specifically endowed man with a mind whose greatest accomplishment was to understand those mathematical laws. And at about the same time, in Italy, Galileo expressed it this way: philosophy, we should now call it science, is written in that great book which ever lies before our eyes. I mean, the universe. But we cannot understand it if we do not learn the language and grasp the symbols in which it is written. This book of nature, said Galileo, is written in the mathematical language. The symbols are triangles, circles, and other geometrical figures, without whose help it is impossible to comprehend a single word of it, without which one wanders in vain through a dark labyrinth. And the French scientist and philosopher René Descartes summed it up in this phrase: whenever I use the word God, you can substitute the phrase mathematical order of nature. The immediate consequence of this concentration on the mathematical side of nature was an amazing decision, one which many of the contemporaries of Kepler and Galileo and Descartes thought to be preposterous. This decision was to divide all our observations of nature into two things: primary factors and secondary factors. The primary ones would concern size, shape, mass, motion, those, you see, which can lend themselves to mathematical and objective handling. And the secondary factors are those which impress themselves on our sense as colors, sound, taste, feeling of heat and cold. And they are the factors which are qualitative and subjective. Now, these early scientists had the audacity to say that science should seek all its information about the world through the primary factors and hold the secondary ones as suspicious sources of illusion. And how does all this work out in practice? Take the case of a falling stone. Science today, progressing in the spirit of Galileo and Descartes, is not interested in the desire of the falling object, its place in the grand scheme of things. To the physicist, the important thing is not where it was found, how to use the stone to hit someone, but the important thing is that once released, it falls with a constant acceleration, causing its speed to increase each second about 32 feet per second. Or think of a rainbow. In terms of modern science, what counts here is not the experience of seeing the rainbow, not the romantic association of purity, the passing of danger. What is important, rather, is an understanding of the rainbow colors as one example of the refraction of sunlight by raindrops, because each color has a wavelength corresponding to it each wavelength having a specific angle of refraction. Probably you feel that this quantitative approach to nature throws away most of what the non-scientist likes and understands best. Of course it does. At first glance, it often seems as if this outlook, which stresses cold mathematics, sacrifices everything of ordinary value. What can possibly be gained by this? Well, nothing less than a key to a door behind which lies a whole new world of knowledge. For only in this way could science have laid bare the fundamental laws on which our universe really operates. Specifically, the quantitative approach has produced 6 gains. The first is, when science began to pay attention to what can be measured and expressed in numbers, the meaning of the words became clear. What is length? Well, if you have a yardstick, everybody can agree what length is because it can be measured. Length itself becomes the reading on a meter stick. Or time. What is time? We can agree what time is if we can read it on a stopwatch. What is pressure? Pressure becomes clear when one has an instrument to measure it with, a barometer. Pressure becomes the reading on a barometer, if you will, at least on the surface. Making such numerical determinations excludes the judgment of tastes or beliefs or other matters of opinion. And this is what makes it easy to teach science without misunderstanding. And it allows scientists of many different backgrounds to get together and solve a problem in a common attack. And this is in part the reason why science has grown so fast. Outside science, agreement is much more difficult to get, partly because the terms used are not, and usually cannot be, quantitative. For example, what is meant by beautiful? Is she beautiful? Of course she is, though perhaps only to another Burmese. Now to the next and equally interesting point, the quantitative approach does not only give you clearer meanings and easier communication, but also lets you more easily arrange conditions so that in the laboratory they repeat. For example, during a long series of experiments at a cyclotron, one has to make quite sure that all conditions of that experiment stay the same. If these conditions of pressure, current, frequency, and so on, can be translated into a reading on a meter, then it's easy to know at all times what the conditions are and how they are changing. In fact, the whole idea of scientific experiment depends on this. With the weapon of measurement and numerical results, one can discover something constant under the confusion of superficial experiences. For example, the slowly moving planets, such as Mars, can be observed night after night against the background of the fixed stars. And if this is done, Mars and other planets seem to make a curious temporary reversal in their path. This makes their motion appear irregular and halting. In fact, the word planet comes from the Greek word for wandering. But with precise measurements of these motions and the interval between the loops, one can begin to make a theory about the motions. One can discover that they merely reflect the fact that both the planet Mars and the Earth, from which it is being observed, go around the sun in regular fashion at constant but different speeds. Or take an example from chemistry. Here are 2 transparent liquids. Inside the larger flask is a solution of lead nitrate. Inside the smaller flask is potassium chromate. Now I have previously put some lead nitrate into the bottom of the flask on the balance. And inside it also I have placed a test tube filled with potassium chromate. The two are not yet mixed. They are both clear liquids. What will happen if I mix them? What will happen if I allow the chemical reaction to proceed. Let us watch. The liquids were clear before, transparent. Now everything has changed inside. Instead of transparent liquids, we have now a solid precipitate. It's yellow, bright yellow as a matter of fact. The consistency has changed. The chemical composition of the materials is different. And yet, if you have a balance to measure it, you will find that before and after, weighing the ingredients before mixing and after mixing together, the weight will be the same in the two cases. Something has not changed, the weight. Well, this is the kind of observation which leads to the most fundamental law of physics and chemistry, the principle of conservation of mass. And note the importance: measurement, mass, not appearance, consistency. Next, a fourth result of relating science and quantity together. The mathematical way of looking at the world produces the feeling in the scientist that he has begun to explain what happens if he has just found the mathematical equation for it. Think of the motion of a projectile, perhaps the motion of a football that is thrown in a forward pass. Why does the football move this way? Surely there are no tubes or guiding rails in space through which it travels. There's nothing inside the ball, no impetus, no intelligence to tell where it goes and how to go. Here the graph represents the path of the ball from left to right. We know that what acts on the ball really is the force of gravity. The best way to express how gravity makes the ball's trajectory curve, as we see it doing, is by means of an equation which says to everyone who can decode its language that the ball will go up and down in a parabolic arc as it moves forward from the hand of the thrower. The equation, then, is a shorthand summary, a description of what actually happens. But because it can be derived from a proposition that gravity acts, the equation carries with it the feeling that it explains the motion, not only describes it. Now a fifth gain, following from this quantitative attitude in science. It's rather surprising. What had previously been written off as merely subjective impressions of judgments which were to be sources of illusion, had a way of becoming primary factors in science. For example, Galileo warned that heat is merely a feeling, a sensation which can't be expressed in numbers, and yet it was an idea of Galileo which resulted in the first thermometer. Here is a model of it. It's nothing but a little glass bulb in which some air is trapped. The stem contains some colored water below it, and when the bulb is heated, perhaps by putting the hand of a feverish patient on it, the expanding air inside is seen slowly to drive the liquid column down. And it is not a long road from this instrument to an ordinary thermometer, an mercury expansion thermometer with numerical degrees along the stem. So heat becomes, after all, not just a matter of sensation, but it can be studied by means of instruments giving numerical readings. And the same happened with color. Color is not just a matter of taste and emotion. With this instrument, a spectroscope, one can assign precise numerical wavelengths to each component of the light. Or in electricity, in the beginning, the amount of charge available had to be estimated, perhaps by the appearance of a spark, or by the shock that one gets by touching the terminal. But of course, not soon after, a meter was developed to show precisely the potential difference between the terminals of a battery. And even music. The sound of a woodwind quartet playing Milo produces, on the one hand, an aesthetic response in the listener, but on the other hand, it can be made to give you numerical results also. It can, for example, be made to deflect a needle on a meter, measuring the intensity of the sound, or the trace on the screen of a cathode ray oscilloscope, indicating the frequency of each of the sound waves. And now, the last and the greatest of the 6 gains of this quantitative point of view. It is the creation of a new belief in the unity of the universe through the results of science. In pursuing the quantitative road to the laws of the universe, Kepler discovered his ecstasy and Einstein his cosmic religion. These are extremes of genius, but every scientist shares some of this feeling. Look, here is what I mean. The light that comes to us from some simple source, perhaps a simple discharge tube, a glass tube filled with hydrogen, excited when an electric spark passes through it, this light can be compared with the wavelength of a beam of light coming to us from a distant galaxy, a beam that may have traveled for billions of years. And what do we find? We find that the light in both cases is the same. That means the material is the same. Stars and Earth have the same elements in common. And the same is true for the laws of nature on Earth and in the stars. The same law governs the fall of a stone here, the fall of a shooting star, the motion of a planet, the motion of our galaxy through space. And so we rediscover that the universe is one. The Greeks and the other philosophers, before the rise of modern science, had to postulate that the universe is one unity. Now, we don't have to assume it. We can find it to exist by experiment. This attention to numerical detail, therefore, merely a curiosity in the days of Kepler, Galileo, and Descartes, perhaps, has given us unexpected results. And so the measuring eye of science complements the other faculty of man, that of the artist, for a full understanding of the world in each of its marvelous aspects.
We have just heard a deeply impressive account of the role of the significance of numbers in science, in physics, astronomy, and so forth. If numbers are so powerful in science, why not use them also in other fields? Then the objects of art, religion, ambition, and love would fall under numerical laws, like the planets and the atoms. You say I'm not being serious? I agree. Yet I would not bet that there have not at times been scientists who made this same proposal seriously. However, if you and I are agreed that we cannot put art and love into numbers, but that as to planets and atoms we can, then this raises an interesting question. How far can numbers go? Can we draw a line and say on one side of this line are the things that can be expressed in numbers, but across the line, numbers become worthless and impotent? Consider a piece of music, a string quartet by Beethoven, let us say. Can we put this quartet in numbers? Certainly we can. Let us look at its score. This quarter note, an F, indicates that a tone of a specific number of vibrations per second must be heard during a certain fraction of a second, another number. And the crescendo indicates that this tone must have a certain intensity, still another number. The musical notation is an extremely clever device to replace an enormous amount of acoustical data by graphic signs that are easy to interpret at a glance. Assuming that this musical score is a correct reproduction of Beethoven's original manuscript, then the 12 pages which contain this particular quartet are a pure statement of fact. The fact that Beethoven wrote such and such musical symbols in a specific order. Now that is not what we mean when we pronounce the words music or string quartet or Beethoven, is it? What springs to mind is the profound emotion we felt on a certain day when we heard the world-renowned string quartet, or perhaps ourselves playing with 3 friends, playing this quartet. Our emotion, we feel quite sure, could not have been expressed in numbers. Not only our emotion, but the beauty of the artist's performance and what Beethoven put of his personality in this quartet These three experiences we know cannot be put in numbers. Well, these experiences all involved what is called a value judgment. I judged that our quartet was playing beautifully that day. However, a visiting music critic may well have thought that our performance was just painful. To a string quartet, even to any serious music, some people react quite negatively. A value judgment depends on who makes it and upon the time and place. A statement of fact, on the other hand, is made by anybody, anytime. For instance, that this specific bar opens with an F, a quarter. But statements of fact, we said, can be expressed in numbers. Of course, that is why they are common to all. Or is it because they are common to all that they can be expressed in numbers? That doesn't matter. The two sentences mean the same thing. Now we can go back to science and say, science is never concerned with value judgments, only with statements of fact. That is why it uses numbers, and why numbers are so powerful. In science, not in art, not in love. Science is not everything. Our emotions are much, much more important to us than matters of fact. They dictate our value judgments. Jack thinks Mary is the most wonderful girl in the world. The rest of us would not agree. But that doesn't matter to Jack. He knows he is right. Jack loves Mary. As the emotional lives of individuals go on, science and her twin sister technology advance steadily in their own domain. Statements of facts expressed in numbers make the huge electric power generators revolve. They make the strong alloys and the pure drugs. By giving up making value judgments, science and technology have acquired the tremendous power which resides in truth. That is the secret of the much misrepresented scientific method.
This is National Educational Television.